Hello everyone. So we are continuing with the molecular orbital theory. In the previous lecture we have discussed what is molecular orbital theory, on what basis molecular orbital theory was developed, was the theory behind, that is linear combination of atomic orbitals, and what are the conditions required for combination of these atomic orbitals which results in the formation of molecular orbital. And after combination of atomic orbitals, how many molecular orbitals are formed and what are the types of molecular orbitals formed, and what is the energy order of different types of atomic molecular orbitals formed. Now, after learning all these things, we are going to apply this molecular orbital theory in explaining the properties of the molecules. So, the first property that we are going to discuss is the bond order. That is, in any given molecule, what is the number of bonds that is formed between any two combining atoms in the molecule, that is known as bond order. So the first application, that is calculation of bond order. So to find this or to calculate this bond order, first thing you have to do is, for the given molecule, we have to write down the electronic configuration in terms of molecular orbital theory by use of the energy order that we have explained, I have given you in the earlier or the previous lecture. So this bond order is defined as half of the difference between the number of electrons present in bonding molecular orbital and the number of electrons present in anti-bonding molecular orbital. This NB, this is number of electrons in bonding molecular orbital, whereas this Na, that is the number of electrons in anti-bonding molecular orbital. So to find the number of electrons present in bonding orbital as well as number of electrons present in anti-bonding molecular orbitals, we have to write down the electronic configuration. After writing electronic configuration, we'll find the number of electrons in bonding, number of electrons in anti-bonding, take the difference, divided this by 2, we get a value that is known as bond order. That is the actual number of bonds formed between the combining atoms in a given molecule. So for any given molecule, we can exactly define what is the bond order of the combining atoms. Then stability. Whether a given molecule is stable or not, we can also define the stability by use of this molecular orbital theory. Now look at this. If the number of electrons in anti-bonding is less than number of electrons present in bonding, or we say if the number of electrons in bonding is greater than number of electrons present in anti-bonding, then the molecule is said to be stable. So let's see why this is so. Now look at this. We have told you earlier, as I have told you earlier, bonding molecular orbital is more stable than anti-bonding molecular orbital, because in bonding molecular orbital there was a constructive interference, that is same phase orbitals overlap to give you a bonding molecular orbital in which there is an increase in density, that is there is an attractive force. Because of this attractive force, the potential energy of bonding molecular orbital decreases as the bonding molecular orbital is more stable, having less energy. If we add electrons in bonding molecular orbital, that leads to the stabilization of the configuration. So more is the number of electrons in bonding molecular orbital, that will be the more stabilized. If the number of electrons in anti-bonding is greater than number of electrons in bonding, then it becomes unstable. Or if the number of electrons in anti-bonding is equals to number of electrons in bonding. Look at this. If number of electrons in bonding and debonding are same, then this difference comes out to be 0. So the bond order is 0. If the bond order is 0, that means there is no actual chemical bond formed between the combining atom. If there is no chemical bond, will the molecule be stable? No, that means molecule cannot exist. So whether a given molecule will exist or not exist, for this we have to write our electronic configuration. Then we have to find if the number of electrons in bonding and anti-bonding are same or greater than or less. If the number of electrons are same in bonding and anti-bonding, then bond order comes out to be 0, so the molecule cannot exist. Bond strength. Bond strength. So now look at this. Bond strength of chemical bond formed between the combining atom depends on the bond order. So more is the bond order, then bond strength will be more. If bond order is less, bond strength will be less. So this bond strength is directly proportional to bond order. So greater the bond order, greater will be the bond strength, stronger will be the bond. Then we can also compare bond length. Now look at this. If the bond order is more, bond becomes shorter. So that means bond length and bond order are inversely related. So if the bond order is less, bond will be a longer bond. If bond order is more, bond becomes shorter. So look at this. This bond length is inversely related to bond order. So greater the bond order, shorter the bond length. Lesser the bond order, longer will be the bond length. So bond order and bond strength are directly proportional. So we can also say stronger the bond, if the bond becomes stronger, then bond length will be less. If the bond is a weaker bond, that means bond length will be more. Then we have, look at this, magnetic property. Whether the given molecule will show magnetic property or not. Now look at this. The given molecule will show paramagnetic if unpaired electrons are present. So while writing electronic configuration based on this molecular orbital theory, if any of the molecular orbital contains any unpaired electron, then that molecule will be showing paramagnetic. That means that will be attracted by an external magnetic field. But if all the electrons are completely paired up, then this will show diamagnetic property. Diamagnetic if all the electrons are paired up, or if there is no unpaired electron. So if there is no unpaired electron, then the substance will be known as diamagnetic, and the substance will be repelled by an external magnetic field. So by use of this MOT, molecular orbital theory, we can find these parameters. Now let's take some examples in which we will find this. So let's start with this hydrogen molecule H2. Number of electrons in hydrogen molecule is, we have 2 electrons. So the electronic configuration is sigma 1h2. The lowest orbital is sigma 1s, and both these electrons is present in sigma 1h. That is the bonding molecular orbital. So if this is the case, now look at this. Bond order, that is half. Number of electrons in bonding, this is bonding orbital, so 2. Anti-bonding is 0. So bond order is 1. That means in between these two hydrogen there is a single bond. Since there is no unpaired electrons, so hydrogen molecule will be showing diamagnetic, no unpaired electron, because both these electron is paired up according to Pauli's rule. Then look at this. So this molecule can exist because there is an actual chemical bond. Take this helium-2, let's take this helium-2. Helium atomic number 2. So we have 2 heliums, so the number of electron is 4. So the electronic configuration is sigma 1s2. So after this sigma 1s, we have sigma star 1h2. We have 4 electrons. So this is bonding molecular orbital, this is anti-bonding. So bond order, that is half. Number of electrons in bonding orbital is 2. Number of electrons in anti-bonding is 2. So look at this, number of electrons in bonding and anti-bonding both are same. So the bond order is 0. Now look at this. In this helium-2, the bond order is 0. If the bond order is 0, then means there is no chemical bond between helium and helium. So this bond cannot exist. So this helium-2 is unstable or cannot exist because the bond order is 0. Similarly, take this lithium-2. Lithium atomic number 3. So 3 into 2, we have 6 electrons. Electronic configuration sigma 1h2, sigma star 1h2, sigma 2s2. Bond order, take this case, half. Number of electrons in bonding, this is bonding orbital, this is also bonding orbital, so we have 2 plus 2, 4. Number of electrons in anti-bonding 2. So if you look at this, electrons in bonding is greater than electrons in anti-bonding, so this molecule can exist and this is stable. So the bond order is 1. So 4 minus 2, 2, 2 by 2, 1. So lithium and lithium means in lithium molecule there is a single bond. So since there is no unpaired electron, so this molecule becomes diamagnetic. Similar take is beryllium-2. Atomic number is 4. 4 into 2, 8 electrons. So we have sigma 1h2, sigma star 1h2, sigma 2h2, sigma star 2s2. So we have 8 electrons. Bond order, number of electrons in bonding is 4, number of electrons in anti-bonding is 4, so the molecule cannot exist because the bond order comes out to be 0. Similarly, we can take this, we'll take some other example. C2 molecule, atomic number of carbon is 6. 6 into 2, 12. 12 electrons. Electronic configuration, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now look at this. This is number of electron is less than 14, less than or equals to 14. So for those molecules in which total number of electron is less than or equal to 14, the order was, after this, pi 2px, pi 2py. So look at this, 2, 4, 6, 8. We have 10, we have 12. So 2, 4, 6, 8, 10, 12. Bond order, half number of electrons in bonding, 2, 4, 6, 8. Number of electrons in anti-bonding, 2 plus 2, 4. So bond order is 2. So between carbon and carbon there is a bond order of 2, double bond. Now in any of this orbital there is no unpaired electron, so this is a diamagnetic species. Take this case, nitrogen, atomic number 7, 7 into 2, 14. This is atomic number 14. Sorry, total number of electron is 14. So we have sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. This is 14. Then we have pi 2px2, pi 2py2. So we have 14. Sorry, 12. After this, we have sigma 2pz2. So total number of electron is 14. So bond order is half number of electrons in bonding, that is 10, 2, 4, 6, 8, 10. Number of electrons in anti-bonding is 4. So look at this, electrons in bonding is greater than electrons in anti-bonding, so this is stable. So nitrogen, nitrogen, the bond between nitrogen and nitrogen is a triple bond. Similarly, look at this, Cn minus, carbon is 6, nitrogen 7, 13, 13 plus 1, 14, 14 electron. Take this, NO positive, nitrogen 7, oxygen 8, 15 minus 1, 14. Then we can have CO, carbon monoxide, carbon is 6, oxygen 8, 14. So these are known as 14 electron species, that is isoelectronic, having same number of electrons. So isoelectronic species has got same electronic configuration and same bond order. So these are all 14 electron species isoelectronic, same electronic configuration, same bond order, same magnetic property. Since there is no unpaired electrons, so these all are diamagnetic. Now let's take some more examples again. Let's take the case of oxygen O2 molecule. Number of electron is 16. So look at it, this is greater than 14. Electronic configuration. So let me write this. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2 greater than 14, then we have sigma 2pz2, then pi 2px2, pi 2py2, 2, 4, 6, 8, 10, 12, 14. Then we have pi star 2px, pi star 2py. Now since these two orbitals pi star 2px, pi star 2p are degenerate having same energy level, then according to Hund's rule both these should be first singly occupied followed by pairing. So without these two orbitals being singly occupied, we cannot place both these electrons in pi star 2px or pi star 2py. That configuration will be wrong. That is the violation of Hund's rule. So whenever we have degeneracy, first degenerate level should be singly occupied followed by pairing. So look at this. This is electronic configuration of oxygen. Now let's find out bond order. How? Number of electrons in bonding 2, 4, 6, 8, 10. Number of electrons in anti-bonding 2, 4, 5, 6. So oxygen, oxygen, this is double bond. Now this is bond order. Now if you look at this electronic configuration, pi star contains 1 unpair, 2 unpaired electrons. One electron is present in pi star 2px, pi star 2py. Due to the presence of these two unpaired electrons, this molecular oxygen is paramagnetic. Paramagnetic to unpaired electrons. So the first important successful explanation of this molecular orbital theory is the magnetic property of the oxygen. So earlier theories cannot explain the magnetic property of oxygen. So it was the molecular orbital theory for the very first time explains the magnetic behavior of paramagnetic nature of this molecular oxygen. So this was one of the first important successful application of molecular orbital theory. Now we take this case O2 plus means we are removing one electron from oxygen. So if you remove one electron, this becomes 15 electron. Now question is from which orbital electron is to be removed. Now look at this. This is the outermost orbital. So we have to remove electron from pi star, that is anti-bonding. If we remove electrons from anti-bonding orbital, then stability will increase because we are removing electron from higher energy anti-bonding orbital. So when we remove electron from anti-bonding, stability will increase. When we add electrons in bonding, again stability will increase. When we remove electron from bonding, stability will decrease. When we add electrons in anti-bonding, then again stability will increase. Now in the first case, look at this. We are removing electron from anti-bonding, so the stability will increase. Let's prove 15. So look at this. From this to this, we'll have same. Then the last one, since we are removing electrons, so this pi star 2px will have 1 electron, pi star 2py will have 0 electron, or we can say pi star 2py has got 1 electron and pi star 2px has got 0 electron. For this bond order, number of electrons bonding as it is, we are removing electrons from anti-bonding, so this becomes 5. So this is 2.5. Now look at this. Removing electron from anti-bonding, bond order increases. As the bond order increases, stability will increase because bond becomes stronger. As the bond becomes stronger, stability will increase. Take this O2 minus superoxide ion. Now minus means one electron is added. So 16 plus 1, 17. Now in which orbital electron is to be added? Again look at this. This is the outermost shell and this contains unpaired electrons. So electron is to be added in anti-bonding orbital. Now since electron is to be added in anti-bonding orbital, stability will decrease. Let's prove. Now as it is up to this pi 2px, pi 2py, configuration will remain same. Pi star 2px 2, pi star 2py 1, or we can also write pi star 2py 2, pi star 2px 1. So 16 plus 1, 17. Now adding electron in anti-bonding, bond order will decrease. So half 10 minus 6 plus 1, 7. So 3 by 2, 1.5. Look at this. When we add electrons in anti-bonding molecular orbital, bond order is decreased, stability is again decreased. Take this O2 2 minus peroxide ion. So 16 plus 2, 18 electrons. From this to this, electronic configuration remains same. So this was 17. Now the 18th electron is to be added to pi star 2py. Now since again electron is added to anti-bonding orbital, again the stability will decrease because bond order will decrease. So pi star 2px2, pi star 2py2. So the bond order comes out to be 10 minus 8. So the bond order comes out to be 0. So O2 2 minus, bond order is decreased. As the bond order decreases, stability decreases. Now coming to magnetic property, the first one is paramagnetic due to the presence of two unpaired electrons. Second, O2 plus still contains one unpaired electron, so this is again para, one unpaired electron. This O2 minus still contains one unpaired electron, so again this is paramagnetic due to the presence of one unpaired electron. O2 2 minus, there is no unpaired electrons, all the electrons are completely paired up, so this will show diamagnetic property. So these are various species of oxygen. So if you look at this, the bond order increasing order or decreasing order. So the lowest bond order is O2 2 minus, then we have O2 minus, then we have O2, then we have O2 plus. So first we'll take a bond order. So bond order is 1, that is 1.5 to 2.5. So bond order increasing order. Stability decreases. Bond order increases. As the bond order increases, again stability also increases. Bond strength. बॉन्ड स्ट्रेंथ अगर बात करेंगे, जैसे जैसे बॉन्ड ऑर्डर इंक्रीज करेंगे, स्ट्रेंथ ऑफ द बॉन्ड ऑल्सो इंक्रीजेस फ्रॉम O2 2 minus to O2 minus to O2 to O2 plus. As the bond strength increases, bond length will decrease. So when we compare the bond length, since the bond order is minimum, so the bond length will be the maximum. So this is the order of bond length. So this is how we compare stability of a given species. So for all this, what we require is we have to write down the electronic configuration. From this electronic configuration, we have to find out the bond order. Once we find out the bond order, we can easily compare bond strength, stability, etc., etc. And to find again magnetic behavior, again we have to write the electronic configuration, and this electronic configuration we have to find if the configuration contains any unpaired electrons or not. If unpaired electron is present, we say that is paramagnetic. If not, we say this is diamagnetic. So this is comparison of the stabilities, bond order, bond length, bond stability of different forms of oxygen. Okay. Oxide ion, superoxide, normal peroxide, molecular oxygen plus, etc., etc. Now let's take up some more examples here. Like this F2 molecule, fluorine atomic number 992 18. So if you look at this, fluorine F2 18 electrons, O2 2 minus, that is O2 2 minus, both are isoelectronic. If both are isoelectronics, the electronic configuration of F2 molecule will be same as that of O2 2 minus peroxide ion. So in both, the number of electrons is 18, electronic configuration is same, so the bond order is 1, and both this does not have any unpaired electrons, so this will show diamagnetic behavior. Take this Ne2, that is neon atomic number is 10, 10 into 2 20. So we have 18 plus 2. So electronic configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we have sigma 2pz2, pi 2px2, pi 2py2, then pi star 2px, pi star 2py. So this was 18. Now then we have sigma star 2pz. So we have 20. 2, 4, 6, 8, 10, 14, 18, 20. Now let's find out the bond order. Number of electrons in bonding 2, 4, 6, 8, 10. Number of electrons in anti-bonding 2, 4, 6, 8, 10. Now since number of electrons in bonding and anti-bonding are same, the bond order is 0, so these Ne2 does not exist. So this is what we call as molecular orbital theory. Now look at this. For all this, what is requirement is we have to know the electronic configuration. Now to know this electronic configuration, we should know the energy order of various molecular orbitals formed. Again, I have given a 2 series for those species having electron less than or equals to 14, or for those molecules or ions for which number of electron is greater than 40. So there is a slight change. So once we have this electronic configuration, we can easily define the parameters. That is a very important application of molecular orbital theory. So all this is coming from linear combination of atomic orbitals. So that was the main point, and this is the application part. So this is a brief summary of the molecular orbital theory concept. Hope you enjoy the class. We'll meet you again.